Hey, physics class. It should be Wednesday for you guys. It's actually Friday for me, but I think it's Wednesday for you. And we're working on 14.1. So you've already taken notes. Please have those available and you can add to them and then respond to the response form at the end of this video saying that yes, you updated your notes, everything's all good. I might ask you a really weird question about something I'm talking about in the video, just so that I know that you actually watched this video. So with that being said, let's talk a little bit more about periodic motion. And periodic motion in general is a repetitive motion that follows the same path, and its cycles are going to take relatively the same amount of time. And so you're familiar with this word periodic from chemistry because we use the periodic table a lot. And so in the periodic table of elements, the elements were all arranged so that they formed a regular repeating pattern with their characteristics. So it wasn't just the table of elements, it wasn't just like a grand list of the elements. They were actually arranged so it made sense, and you had like groups that had several characteristics in common. So it was the periodic table of elements. And anything that recurs at regular intervals is periodic. For example, a newspaper is a periodical because most newspapers come out daily. Many magazines, I know hardly anybody gets print magazines anymore, but typically a magazine would come out once a month, and that is also a periodical. And so when we have periodic motion, again, regular repeating motion, and you should have like the same time to complete each cycle. So let me give you a few examples of periodic motion. Of course, we have pendulums, springs. Those are the two main ones we'll be talking about. But also like musical instruments. When you have like a stringed instrument like a guitar or a violin or a cello, something like that, the strings are actually vibrating in periodic motion. And even if you don't have strings, like a clarinet or a flute, you vibrate a column of air inside the instrument, and that gets vibrated in periodic motion, which is really cool. And then also just a tree swaying in the wind or a leaf swaying in the wind. If it's a sustained wind long enough for you to keep track of it, that's an example of periodic motion. Bridges can sway in periodic motion, as you saw in the video yesterday. And also just waves in general, like sound waves, light waves, any electromagnetic wave for that matter, can have periodic motion that has repeating cycles and things like that will go on and on. And so we'll talk about waves more in another chapter, which is pretty cool. All right, let's go over some of the key terms in this section. One of them, of course, would be period. Like, how could you possibly talk about periodic motion without talking about a period? A period is a specific time that it takes for something to make one complete cycle. Like the hand on a clock will make one complete cycle as it goes around. And so the second hand has a period of 1 minute. I know we've talked about this before. The symbol is capital T because it is a type of time, but it's a special type of time. And then the SI unit should be the second for our problems in this chapter. And so let me go ahead and talk about equilibrium position. So I have this pendulum, and it's not a real pendulum. It's actually a necklace that I am going to use as a pendulum because it was just really fast to do that. But I have a heart charm. Now you can see it right there. And it's just, I just like did the necklace out so it was suspended at the bottom of the necklace. But this is a really quick pendulum. And when this pendulum is just kind of there, it's like resting, it's in its equilibrium position, and my hand isn't super steady, so it's moving around a little bit. But when gravity's pulling it straight down, that's the equilibrium position for this pendulum. And then if I had a spring, I don't have a spring to show you, so sorry. But if you can imagine a spring that's just kind of there and it's not being compressed or stretched, whatever its natural position is, that's its equilibrium position. And then you could press it in or you could stretch it out, and that would be out of its equilibrium position. And so amplitude is the amount, like the length that it's compressed or stretched, or in the case of a pendulum, like if you bring it back, out of the rest position, you could bring it back for a small amplitude or a large amplitude. And so that's the distance from its equilibrium position. Okay, and then, let's go on to specifically simple harmonic motion. And we like to abbreviate this because it's kind of long. So often you'll see it written SMH. And this is specifically any system in which the force acting to restore the object to its equilibrium position is directly proportional to its displacement. And so basically something in simple harmonic motion, we would say friction is not causing it to slow down. Like it's very consistent, regular, dependable, and like a real pendulum, if I set this in motion, like we like to study pendulums for simple harmonic motion, but if I set it in motion, like it's going to slowly, like the amplitude will get smaller and smaller over time because there's some vibrations and some friction and some internal stuff going on. And so you can see that it's already starting to come to a stop. But something in true simple harmonic motion, like once I set it in motion, it would continue on and on and on and on, like for eternity, unless another force acted on it. And then let's talk about what we call Hooke's law. And hang on a second, this like rubbed off a little bit because I had all these little boards stacked up together. So Hooke's law specifically applies to springs. So I drew a little slinky spring right there. But Hooke's law has a formula right here. And basically, I'm not going to read it, but like it's one of those where if you read it, it says what the formula says anyway. And so the force exerted by the spring, the force exerted by the spring is equal to negative K, which is the spring constant. I'll talk about that in a minute, times the distance that it was stretched. And so we're actually not going to do any math problems associated with this. I know y'all are very sad about that. But I did want to talk about the spring constant because every single spring is a little bit different. Even if you had like a bunch of pens and you unscrewed them all and you took all the little springs out of the pens, like each one of those could be slightly different. They're likely to be rather similar because they're made from the same factory, the same metal, whatever they used, aluminum, whatever it was. But they could vary slightly, especially when you get out a lot of decimal places. But the spring constant depends on the temperature the spring's at. It depends on the stiffness of the spring. It depends on the materials that make up the spring. So many different things go into that. And it's kind of like, remember when we were studying friction and we had like coefficients of friction and like different materials would have different amounts of friction. Like if it was carpet, it would be a lot more. And if it's like a hardwood floor, it would be a lot less. It's kind of sort of like that concept that it just depends on the material itself for the spring constant. And so again, we are not doing Hooke's law problems with this. I know y'all are super sad about that, but you'll get over it, I promise. All right, let's talk about how all springs don't even obey Hooke's law. So they found that Hooke's law is pretty reliable if you have like minimal amplitudes, but when you get into large amplitudes, it just kind of all goes out the window. And then not all springs are even close to following Hooke's law. Like if you suspend something from a rubber bands are so flimsy and they tend to stretch out over time. Like don't even go there. Like don't even try. So I think that's all I need to say about that. And then let's talk about simple pendulums. And so I already showed you like my makeshift heart necklace pendulum there. But a pendulum is any kind of mass, preferably around like spherical mass. We call this a bob. That's what it's really, really called. And it's suspended by a rope, a string, a chain, maybe like a necklace chain, whatever you want to suspend it with. And then the length of a pendulum, I do want to point this out so I have a marker ready. When we measure the length of a pendulum, you would go from the top, wherever it attaches to something, and then you would do it to the center of whatever the mass is. And this could be a little bit trickier. Like I would say the center of mass even, because like this heart is a little bit different. So the center of mass for the heart probably is a little bit higher than the actual center of it. So you would use the center of mass. And then we're going to do an L for length. And I did a cursive L. That's pretty standard because if I do a print L, it's going to look like a 1, which could be really bad. So that's what you need to know as far as measuring things on a pendulum. And then the period of a pendulum, we will do some math with this, but I'm not even going to show you. There's a sample in the book on page 387. It's really, really easy. I think that you'll be fine with it. And so when I do like the theory questions on this, I'll just include a couple of math questions. I think that y'all will be absolutely fine with it because it's pretty simple math. But here's the formula for the period of a pendulum. So the period of the pendulum, which is T, is equal to 2 times pi. And of course, just hit your pi button on your calculator. It's the 3.14, blah, 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 blah. Just hit the pi key on that. And then times the square root of the length. Remember, that's going to be the distance from the top to basically the center of whatever mass is suspended, divided by g, because gravity is really important in pendulums. And so for g, remember, we're going to use 9.8 meters per second squared. So that's another reason why like your period needs to be in seconds, because we're using this value here, the 9.8 meters per second squared. And also the length needs to be in meters to match with this. So if you're given a length in centimeters, which could very well happen, please convert it to meters by dividing by 100 or moving the decimal place over 2 places to make it smaller. Okay, and notice what's missing in this formula. Like, a lot of people think that if you had a more massive object, the period might be longer or shorter. But it really doesn't seem to matter how massive the object that is suspended is. And it also does not seem to depend on the amplitude. And so you can test this out like at home if you want to. You can get something and suspend it from a rope or string or yarn, whatever, and you can test it out. You can launch it from different amplitudes and then time the period. And the period for a pendulum would be like from here to here and back again, because that's one cycle. Like if you just go from here to here, that's only half the cycle. So the period should be from here to here and back again. That's 1, 2. And so you could even test it out. Like does that really hold true? If I launch it from way out here, will it come back and forth? See, it's already slowing down so much though, it's ridiculous. Or if I just launch it here, will it be the same amount? And then I'll give you a little hint on what you can do to make it go faster or slower. Watch this. If I draw it up, watch what happens. And then if I lengthen it, watch what happens. Very significant difference. So that could help you out later on when we talk more about how to speed things up. So I think we covered everything. Oh, resonance. I'm not going to say a ton about resonance. They actually introduced resonance in the video, but basically the idea behind resonance is everything has a natural vibration. Remember, the internal particles of an object are moving constantly, and they just kind of have like a collective vibration. But if something comes along and gives extra energy, you can actually increase that amplitude pretty easily. And so an example of this would be if someone other than you is swinging like in a swing, and you push them, you know when to push them. You figured this out from life, on a playground, right? Since you were like 3 or whatever. You push them at just the right time and it makes them go higher. Well, that's the same with sound or any type of vibration like that. If there's a push at just the right time in the cycle, it'll actually naturally increase that amplitude. And so another example was the bridge that they showed, the Millennium Bridge in London. The people were walking and it was swaying back and forth, and like to keep their balance, they would lean into it, and so it just made it all the worse. There was actually a bridge in Tacoma, Washington that completely collapsed because the wind was making it sway and resonance happened, and the whole bridge tore apart. You can look up a video on that. I might actually assign to watch that video later when we talk a little bit more about resonance, because it's pretty cool and it really happened and pretty scary. So engineers have to watch out for that when they're building bridges. But you've probably noticed it just sitting there in your house. Like if you have a picture frame on a window, or not window, picture frame on a wall, and then like all of a sudden a truck goes by outside and the picture frame starts vibrating randomly. Like that's because the energy of the truck outside matched the energy of in the frame somehow, and it caused it to vibrate noticeably now, and you can actually hear it. So things are vibrating all the time, but if they get like an extra input of energy at just the right time, it's going to cause an increase in the amplitude. Another good example, I know this is the last one, I promise, is like if you have like a crystal glass, you've seen the people like sing like an opera voice, and basically if they match the frequency in the crystal glass, then they can make it like come out of its arrangement and shatter. And so that's something that is real life and really happens too because of resonance. So pretty cool stuff. And please don't forget, now that you've watched this video, hopefully you updated your notes as needed. And I'm not going to work out the math because it's so easy. If you want to look at the sample problem on page 387, take a look at that. I feel fully confident that all of y'all would be able to easily do that and respond to this video, and we'll move on with some questions tomorrow.